expressing Fourier transforms. So, a Fourier transform is defined as the integral of the time domain signal times e to the minus j omega t dt. Okay, and this is often expressed with this calligraphic f, a bracket of the signal, time domain signal x of t. Okay, so this is a shorthand for Fourier transform. So on the other hand, right, if you take 1 over 2 pi, the integral of the spectrum times e to the j omega t, you have the inverse Fourier transform that gives you the time domain signal. And the shorthand for this is the calligraphic f with this inverse. Okay, so this represents the inverse Fourier transform. Okay. So if x of t and capital X forms a Fourier transform pair, then we often express the relationship like this, right? We have a double-headed arrow with a calligraphic f on top. Okay, so this is just a couple of examples based on what we showed before. So we know that this single-sided exponential, decaying exponential, has a Fourier transform that is 1 over a plus j omega. Right? So we say that this with calligraphic f is equal to 1 over a plus j omega. Okay, and similarly for the inverse Fourier transform. Okay, and since this and this forms a Fourier transform pair, therefore we use this expression to denote this relationship. Okay. Now next we want to show a series of properties of Fourier transforms that are almost the same as what we showed for Fourier series representation. Okay, so you should have the same insight and the same should be able to derive them using similar approaches. Okay, so these properties include things like linearity, time shifting, conjugation, right, differentiation, integration, and so on. Okay. Now let's try to go through them one by one, right? They're mostly the same as before, okay? So linearity, right? Suppose you have, suppose that you have two signals, x of t and y of t, which has Fourier transforms, capital X and capital Y respectively. Then a linear combination of the two time domain signals has a Fourier transform that is equal to the same linear combination of their corresponding frequency domain signals, okay? All right, so this is straightforward, so I'm going to omit the proof for this, but you can try to do this yourself, okay? Now the second one is time shifting. Time shifting says that if x of t has Fourier transform capital X, then a time shift of a shift in the time domain signal corresponds to a phase shift in the frequency domain, okay? So if you remember, for Fourier series representation, this is also true, right? For a periodic signal x, a time shift corresponds to a phase shift in the Fourier series coefficient, okay? So, right, we can do a similar proof, right, just to let you know how we can show this. Right, so we know that x of t minus t naught, okay, is equal to 1 over 2 pi x of j omega times e to the j omega t minus t naught d omega. Okay? So by the inverse Fourier transform, we know that x of, let's say, x of tau is equal to 1 over 2 pi, the integral of capital X times e to the j omega tau d omega. Okay. Now I'm just substituting tau with t minus t naught, right? Therefore, this relation comes directly from the inverse Fourier transform. Okay. Now I can split this exponential into the product of two exponentials, so that this becomes 1 over 2 pi x of j omega e to the minus j omega t naught times e to the j omega t d omega. Okay? So by the inverse Fourier transform, we can then see that this part should be the inverse, this part should be the spectrum of this delayed signal. Okay? So hence, the Fourier transform of x of t minus t naught is equal to x, capital X of j omega times e to the minus j omega t naught. Okay. So if you want, right, you can, if you want to see the impact of this, right, you can split this original spectrum into the magnitude and phase. So if you do that, you will see that you get the same magnitude, but only the phase is adjusted by omega t naught. Okay? All right? So this shows you that a shift in the time domain, a time shift, right, has no impact on the magnitude, but actually has a shift in the phase of the signal. Okay? All right. Let's look at this example. So in this example, we have x of t that looks something like this. Okay? Now we can actually split x of t into, the summation of two waveforms like x1 and x2. Okay? So here, if you define x1 as this square wave from minus 1/2 to 1/2, and 1, right, in between, right, 0 everywhere else. And if you define x2 as a square wave from minus 3/2 to 3/2, then you can combine these two, shift it to the right to this position here, then you will get x of t. Okay? So x of t can be written as 1/2 x1 t minus 2.5 plus plus x2 t minus 2.5. Okay? So x2 t minus 2.5 moves the center of this to 2.5, right, to get this. Okay? Right, so this is x2 t minus 2.5, right? And this part on the above is half of x1 also shifted to the right by 2.5. Okay. So this part here is 1/2 x1 t minus 2.5. Okay. Now, the advantage of writing x of t as a linear combination of x1 and x2 is because we know what are the Fourier transforms of x1 and x2. Right? x1 and x2 are square waves, so their spectrum are sinc functions. Okay. So from previous study, we know that the Fourier transform of x1 is 2 sine omega over 2 omega, okay? And the Fourier transform of x2 is 2 sine 3 omega over 2 omega. Okay? And both of these are by example 4.4 that we just showed. Okay. So with this knowledge, right, we can then obtain the Fourier transform of x of t as a linear combination of the Fourier transforms of delayed versions of x1 and x2. Okay. So therefore, the Fourier transform of x of t gives you 1/2 x1 of j omega times e to the minus j omega 5 over 2, right? 1/2, 1/2. A delay by 2.5 corresponds to a phase shift of omega times 2.5, okay, which is 5 over 2. And similarly, for the second term, you get x2 j omega times e to the minus j omega 5 over 2. Okay? And then x1 and x2 we have here, so we can just plug this inside. And this will give us, okay, e to the minus j omega 5 over 2 of sine omega over 2 plus sine 3 omega over 2 divided by omega. Okay? Okay. So I hope you can see that utilizing this linearity property and the time shifting property makes analyzing the spectrum of x of t much easier. Okay? So if you want, you can go back and try to compute the Fourier transform of x of t directly. Right? I believe you can still do that, but it will be a little bit more tedious. Okay? Okay. This follows directly from the inverse Fourier transform formula, right? Because okay, so maybe it's easier if you view this as a signal y of t, then this part will be y of j omega, right? 可以吗？ So this follows directly from from this formula here, right? So this part inside the integral, right? This part inside the integral is the Fourier transform of this signal. Yeah. So if this is x of t minus t naught, then whatever is contained here should be the Fourier transform of x of t minus t naught. Okay? 可以吗？可以吗？啊？什么？你说？Okay, so suppose I'm using y, right? You have this. Okay. So what I'm doing here, okay. What I'm doing here is I'm just treating y of t as x of t minus t naught. Right? So this is x of t minus t naught. Okay. So whatever is here will be the Fourier transform of this. Okay. All right. So, any other questions? OK， 有没有其他的问题？对啊，有同学问问题蛮好的，这样子可以让我知道说哪边没有讲清楚。OK， 好，那没有问题的话，我就继续哦。OK。Okay, so the next property is, conjugation. 这个吗？哦，少一个2 ，OK, sorry. 所以我可以把它写到外面去嘛，对不对？哦，没有，这里少一个2。这样对吗 ？OK， 好，谢谢。Okay. All right, so with this property, we want to show that if x of t has a Fourier transform that is capital X of j omega, then the complex conjugate of x of t will have a Fourier transform that is the complex conjugate of capital X with a reverse of the frequency. Okay? Now you can show this through straightforward computation as well. So suppose we compute the Fourier transform of x star of t. Okay? So this by definition is x star of t e to the minus j omega t dt. Okay. Now we can bring this complex conjugate outside of the entire thing. Suppose we bring the complex conjugate outside, then what we have inside should be the integral of x of t e to the, because complex conjugate is brought outside, therefore what I have remaining should be e to the j omega t. Okay. Now instead of writing e to the j omega t, let me write it as minus j minus omega t dt. Okay? So the two minus signs cancel out, so this is still e to the j omega t. Okay. But the advantage of writing it this way is because the integral inside here is then the Fourier transform of x of t at frequency minus omega. Okay? So inside here, we have x of minus j omega, and therefore with the complex conjugate, okay, we have this. Okay? So this shows our result here. Okay. Now we can further show that if x of t is real, okay, which means that x of t is equal to x complex conjugate of t, then it follows that the Fourier transform should be equal as well, and therefore, so then x of j omega should be equal to x star of minus j omega, which means that the spectrum is conjugate symmetric. Okay? And you can see that this is the same property as in what we showed for Fourier series coefficients. Right? So for periodic signals x of t that is real, you can show that the Fourier series coefficients are conjugate symmetric. Okay? Okay. So this is an example here. So we have x of t that is a single-sided decaying exponential. Okay. So we know from previous example that the Fourier transform of this is just 1 over a plus j omega. Okay. Now you can show that, right, if you look at x of minus j omega complex conjugate, right? This is equal to 1 over a minus j omega complex conjugate, and is equal to 1 over a plus j omega, which is x of j omega. Okay? So indeed, you can see that if x of t is real, its frequency domain must be conjugate symmetric. Okay? So this is indeed conjugate symmetric. Okay? Now, furthermore, right, if you have x of t that is real, right, then, right, as we just showed, this spectrum is conjugate symmetric, right? So what this means is that this x of j omega should be equal to x of minus j omega complex conjugate, which means that it should be equal to the real part of x of minus j omega minus j of the imaginary part of x of minus j omega. Okay? So if you don't have this complex conjugate, it should be the real part plus the imaginary part, right? But because of this complex conjugate, this plus becomes a minus, okay? So if you compare the two, this means that the real part of x of j omega should be equal to the real part of x of minus j omega, okay? Meaning that the real part of the spectrum should be even, okay? And the imaginary part should be odd because of this extra minus sign. Okay? So hence, the real part of x of j omega is equal to the real part of x of minus j omega, meaning that the real part is even, and the imaginary part is odd. Okay? Now you can show something similar for the magnitude and the phase as well, okay? Because of the conjugate symmetry for real signals, right, this means that this should be equal to x minus j complex conjugate, which has a magnitude absolute of x of minus j omega, and a phase that is minus j, the phase of minus j omega. Okay? So originally, without this complex conjugate, it should be, just be the magnitude times exponential of the phase. But because of this extra complex conjugate, I have a negative sign here in front of the imaginary part. Okay? So therefore, if you compare the two, you will see that the magnitude is real. The magnitude is even, and the phase is odd. Okay? So here we can see that the magnitude is even, and the phase is odd. Now, furthermore, right, if you know that x of t is not only real, but is also even, so if you know that x of t is not only real, but also even, right, then you can also show that the spectrum is also real and even, okay? And this property is also the same for Fourier series coefficients, right? If you recall that in that case, for a periodic signal x of t that is real and even, the Fourier series coefficient will also be real and even, okay? So this is also, pretty straightforward to show. Right? We just start from this formula for the Fourier transform. This is x of t e to the minus j omega t dt. Okay? Now, since this is even, x of t should be equal to x of minus t. So I can write this as x of minus t e to the minus j omega t dt. Okay. Now let's do a change of variable where we switch tau, we set tau equal to minus t. So in this case, x of minus t becomes x of tau. Okay. So in this case, we have x of tau e to the, we should have, minus t becomes tau, so we should have e to the j omega tau. But instead of writing e to the j omega tau, let me write it as e to the minus j minus omega tau. Okay? And this is exactly the Fourier transform at frequency minus omega. Okay? So this shows you that the spectrum is even. Okay? But we also know that if x of t is real, then it also should be conjugate symmetric. So this is also equal to x of minus j omega complex conjugate. Okay? So since this is equal to its complex conjugate, this means that the signal in the frequency domain is also real. Okay? So hence, x of j omega is also even, let's say real and even. Okay? Okay. So any questions here? Okay. So we know that if a signal x of t is real, then it is conjugate symmetric. And we know that if it is further even, right, not only real but also even, the spectrum will be both real and even as well. Okay. Now, if x of t is instead real and odd, then similar to the Fourier series coefficient, the spectrum will be pure imaginary and odd. Okay. So by this property, you can also infer the following. Right? So suppose that you have a real signal x of t. So it's critical that it must be real. Okay. So if you have a real signal x of t, we learned before that for any signal, we can always write it in terms of an even part plus an odd part. Okay? Now, for the even part, this is even and real. So this even part must have a Fourier transform that is real. Okay? And the odd part must have a Fourier transform that is pure imaginary. Okay? So when you perform the Fourier transform of x of t, you will find that the real part of the transform actually corresponds to the transform of the even part, and the imaginary part of the transform actually corresponds to the transform of the odd part. Okay? So this is an interesting consequence of this property. Okay. All right, so let me stop here. The remaining of this part 1 of chapter 4 are just, the remaining properties. So we need to go through this differentiation.